Hello. It is Sunday night. It is December 1st. This is a lecture for tomorrow, December 2nd. I will post this on D2L when I'm finished. I want to just end this semester discussing molecular orbital theory and just to give you a chance to get kind of understanding the material before you see it in inorganic. And so way back when we did bonding in Gen Chem, there were two types of theories. We only gave you one in Gen Chem. That was kind of valence bond. And the other one is molecular orbital theory. Valence bond, for all that it's worth, is really just hybrid orbitals, sp2, sp3, sp. And that works really well for organic. It explains a lot. But in reality, MO theory is kind of the theory that we use when we want to look at structure, molecules. And it's really, as Atkins says, and this is section 10b, it really is kind of like the modern discussions of bonding uses MO theory. And so what is MO theory? And really what we're thinking of, in this case, I'm just going to deal with a hydrogen atom, and we're just going to deal with today 1s with the first hydrogen, and we're going to deal with 1s for the second hydrogen. And the question is when we bring these two together, we know that a bond is formed. And so kind of what we're trying to figure out is how does this work using quantum mechanics? And really what we're going to look at is that when we put these two together, you're going to get the following. We're going to get basically your wave function is going to be some sort of normalization times the atomic orbitals from the first hydrogen, and time plus and minus the atomic orbital from the second hydrogen. And so you can see what's going to happen here is that all of a sudden, what are we looking for in reality? What we're looking for, and we've talked about this in previous editions, is what we see is really psi squared. And so what you're going to get and what we're going to see is you're going to get two possible outcomes when we square this. And one of the outcomes is going to be the following. Psi squared equals n squared times a squared plus b squared plus 2ab. And so, and the other outcome is going to be n squared times a squared. Everything's the same, but the big difference is one is positive and the other is negative. And so what you're going to see, and I don't really like using these terms, I like this term, we're going to call this a bonding. And we use this term and I don't like it. It's anti-bonding. It really is not anti, it's just a bonding doesn't occur. So let's take a look at the beginning. So we have this, and really what we're interested in, this is why we use iPads. Let me change the color so it's not as, what we're really interested in is going to be these two terms right here, okay? One is positive and the other one's negative. And so if we go to the handout, what you're going to see is the following. We're going to go up, and what you get is these are the two possibilities. When it's positive, 2 plus AB, you see that you're going to basically get a region where we have constructive interference. Once again, positive, it means constructive. And when you have a negative region, minus 2AB, you get destructive. And so notice when you have destructive, or when they basically cancel each other out, you're going to get a region right here where it's basically a node, okay? And so if we take a look and we're going to look over here. If we take a look at the profile, the amplitude, you'll see that basically what you get in between is bonding. And what you get over here is, and I'm going to use anti-bonding, but it's really just this destructive interference. And so your two profiles, if we take a look again, you have the following. You can have, this is the positive, and this is an overlap, and this is bonding, and this is the negative, and this is anti-bonding. Okay. And you can see it in different forms. You can see it here for the anti-bonding, or you can see it here in terms of electron density calculation. And so what you get, and we're going to draw one of these, is the following. You have the A hydrogen 1, and you've got the B hydrogen 2. And so when you have something that's constructive or bonding, you'll see that because it's positive in overlap, it's less energy. Boom, 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 boom. But then when you have something that's anti-bonding, it's more energy because it's destructive interference, and you get something that looks like this. Okay, and so those are the terms that we can use. And so this right here is going to be your bonding part, and this is your anti-bonding part. And so really it's just comes down to, once again, it's a linear combination, but because in quantum mechanics, in order to see or to get the probability, what we end up doing is we end up squaring it. And when you end up squaring it, that plus minus becomes a linear combination where one is minus and one is positive. One is positive and the one is negative. And so just a few terms for clarity, and we'll get into this in a second, but really what we're doing is we're reproducing this chart right here. Highlighter time. Yeah, this is, this is the great thing. What we're reproducing is this figure here. The important thing, though, is we're going to label this sigma, and usually it's labeled with, excuse my second, sigma 1G. Shoot, Professor Dudek is using erasers. Okay, this is sigma 1G. And then this usually is labeled 1 sigma U. I don't necessarily like that. Some of the terms that you end up seeing, you'll see that Atkins uses it here. I personally like to use the star. You'll see this as sometimes sigma G, and then you'll see this as sigma U star. And the star really just means anti-bonding, okay? And so what are we looking at is when you have something that, like when you have an overlap here of the two, still can't draw a perfect circle even on an iPad, what you see is when you have a positive overlap, and so this is positive 2A, when you, if you go from 1 here to here, it's plus. You don't have no inversion, and this is what we call no inversion. We call this even, and the Germans call it gerade. Okay, so you don't go from positive to negative, but when you have a minus 2A, and you have this is positive and this orbital is negative with your kind of an antibond in the between, when you go from here to here, you have an inversion. It's odd, and we call it ungerade, and that means odd symmetry in German. Okay, and you get something that looks like this. Okay, and so what we have is now what we can do is we can start looking at bonding. So bond order, okay, in all of this is 1/2 the number of bonding electrons minus the number of anti-bonding electrons. And so what I want to do is just to go over this for a second is the following. Let's take a look at a few different cases. We're going to do H2, okay, and then we can do other species, but what we could do is also H2 and HE2. So we know that H2 occurs. The question is, what happened to why don't we have HE2? So let's take a look at first at let's take a look at H2. Okay, and so we have A, we've got B, we got your bonding. Oh, I should probably dash it. Okay, so then we dash it. Yeah, boomers with technology. And then, so what you get is the following. So how many electrons do you have? You have 1 up and 1 down. And so this, once again, this would be the sigma G, the sigma U star. Okay, and this would be your bond order would be 1/2 2 minus 0. And so from there, you can clearly see that your bond order is going to equal 1. So you get a single bond in this process. And so the other thing we can do is we can look at He2. So why doesn't helium do this? And so you'll see we'll do He2. And so He2 is going to have 2. Oh, I should have just come up here. There's 1 electron up, and there's 1 electron up. Okay. Helium has 2 electrons, 2 electrons. And so when we bring this to here, bum, 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 you got to bring in the sound effects. What you see is the following. That you have 4 electrons, 1 up, 1 down. But now, because you still have to populate, you have 2 electrons in the anti-bonding. So the bond order for He2 is 1/2 2 minus 2, which equals 0. So the reason why we don't have a helium diatomic is because in the end the bond order is 0. There's no reason for it to connect. And so you can do some bizarre things if you really wanted to in the world of chemistry, and with a little bit of work in terms of either using high-powered laser or magnetic field. What happens if we have helium-2 plus? And so you can see what's going to happen if you have helium-2 plus. You get the following. Okay, and then dot, 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 dot. So helium-2 plus, you would have 3 electrons. And so what you would see is that you'd have 1 up, 1 down, and then only 1 electron in the anti-bonding. And so your bond order for that would be 1/2 2 minus 1, which equals 0.5. So you would have this weakly bonded complex that would basically break down if you put a little bit of energy into it. So you can play some really interesting games. But I wanted just to start it off, this lecture, dealing with just the s orbitals, and what we're going to do on Wednesday is I want to take a look at the p orbitals. And so you'll see that basically it's rough. It's going to be the same thing, just a little different because you have, we'll put the highlighter out for the last time. You've got some center of inversions here. But in the end, you'll see that there's bonding and anti-bonding. And so I'm going to stop here. I'm going to post this. And so your in-class problem, which is on D2L, and which I also sent, really is just going to ask you about describing the difference between these two figures right here. And just so, what's the difference? And it's all right there. I hope all is well. I do apologize for not being there. Hopefully I'll be there later in the week. Hope all is well. If you do need anything, please do not hesitate to contact me. Life's pretty quiet up here, and I hope to hear from you soon. Have a good evening.